My name is Kristoffer Sahlin, and I'm an assistant professor at the Department of Mathematics at Stockholm University. And I will present Strobemers, which is an alternative construct to spaced k-mers and k-mers to do sequence comparison. So why do we want to find shared regions between sequences? Well, it's a fundamental step used in many bioinformatic applications, such as mapping reads to a genome, clustering reads together, finding overlaps between reads in genome assembly, and many other applications. So we can find, for instance, exact sequence similarity by doing pairwise alignment, but it is in general slow, where it's roughly quadratic complexity, where n is the query length and m is the reference length. So usually what is performed is that some fast approach to index or pre-process the reference sequences so that we can query quickly. So let's look at an example of using k-mers. So we have a sequence 1 here, and if we construct all the k-mers from this sequence, we have something as the following. Now, if we have another sequence that are similar to sequence 1, but with 2 substitutions and 1 deletion, we have that most of these k-mers are affected, so meaning that we're left with only 5 k-mers that are shared between the 2 sequences. And so in general, k-mers are fast to create and they yield many matches, but they are somewhat sensitive to substitutions and indels. And also the matches are highly clustered, which is what we see in this example. We have most of the matches in this region. So spaced k-mers is designed to alleviate some of this. So in this protocol, we fix k positions within a window of L positions. And here, if this hash denotes the fixed position and this symbol denotes the wildcard position, we can sort of sample k-mers with this pattern. And looking at our previous example, we have the following 3 shared spaced k-mers between the 2 strings. So in general, here we can see they have fewer matches than k-mers, but they are sort of less correlated in their spacing on the 2 sequences. So in general, spaced k-mers, they're good because they can match over substitutions. They have less correlation between matches than k-mers, but they do not handle indels well. So another technique is neighboring minimizer pairs. And I won't go through minimizers in detail, but roughly it's we hash k-mers into integer values, and the minimizer is the k-mer with the smallest value from W consecutive values. So we can create, for instance, minimizers of size of k2 on the 2 sequences. And so this would be the minimizer sketches. Now, a neighboring minimizer pair is where we pair up the minimizers, the 2 consecutive minimizers on the sequences. So for instance, AC to AC is a neighboring minimizer pair on sequence 1. AC to CT is another one, and so on and so forth on these 2 sequences until we have a set of neighboring minimizer pairs. Now, the novel thing here is that they are constructed so that some of these neighboring minimizer pairs might span or match across indels. So this is really a nice feature. However, we may also see that due to mutations within or indels within the 2 sequences, this may offset the minimizer landscape, meaning that a lot of the neighboring minimizer pairs will not match across sequences. So there's some sort of correlation here that we want to get rid of in these neighboring minimizer pairs. So this is sort of partly why we designed Strobemers. So what is a Strobemer? Roughly speaking, it consists of n linked short k-mers or strobes of length s, where the first position of the strobe is fixed, and then the rest are chosen based on some downstream window. So let's look at an example. So the parameter that goes into this is the number of strobes, the strobe length, and a minimum and maximum offset to the next strobe. This figure here shows an example where we have 3 strobes, each of length 2, with some window size. So here we have the strobe length, and the window where we sample the next strobe is limited with these window parameters. For the first strobe, we count the minimum offset from the position of the first strobe. So this will be 1, 2, 3 positions downstream where we sample the next strobe. For the remaining strobes, we count it as the offset to the end of the next window. So 1, 2, 3 to this one. And this is really all there is to create these strobemers. But how are these next strobes created? So we'll do this based on some sampling techniques. So these are the windows for sampling where we sample the next strobes. Now the way we sample, we can do this with some different protocols. So I designed 3 different protocols: min strobes, rand strobes, and hybrid strobes. I will only go through rand strobes here in the interest of time. So in rand strobe protocol, we sample the next strobe based on previous strobes. So how does this look? So in this example, we are going to create strobemers with 2 strobes of length 2. So the first one, as I noted, is fixed. So now we're going to select the next one from this window. We consult the following function to do this. And this is h is a hash function and q is some integer, positive integer value. So for instance, let's say under lexicographical hash function, we have that h to this function would hash this string to position 4. And then we have that the 3 potential strobes in this window will hash to some other values depending on the hash function. So we have GA hashes to 8, for instance, AC to 1, and CT to 7. Now, if we plug in the numbers into this function, we see that they create different results. And we select the strobe that creates the minimum result that minimizes this function. So here we're going to pair up CA to AC. So this will be our first strobemer in this example. Now, the nice thing with this is that for the next position, AC, this has a different hash value, meaning that if we plug in the new numbers of the 3 new potential strobes in this window, we have a different outcome. In this example, we have that TG minimizes this function. So meaning that AC is no longer, in some sense, a minimizer in this window, but with this prefix, we have TG is the minimizing value. And so on and so forth across the string. And so this sort of yields a more random sampling of subsequences. And with some probability, we may have that some of these strobes are spanning both mutations and insertions and deletions. And of course, we can create these protocols by linking together 3 strobes or 4 strobes, etc. So the positive thing here is that rand strobes, they match over both. They can match over both substitutions and indels. They also produce less correlation between matches compared to what we saw with neighboring minimizer pairs where the minimizers are fixed. However, how about the time to generate them? So it looks a bit scary here. So if we abstract over the details of the hash function, we see that in general, k-mers take O of m time to hash if we have m is the sequence length. Now for strobemers, we need to minimize over something over the n-1 consecutive remaining strobes within some sort of window. So this looks scary. However, with some efficient implementations in compiled languages, this is fairly quick. So I described strobemers as a modulo, as it is more intuitive, but we can do this, for instance, with bitwise AND operator, which is much faster than modulo. So we would replace this with if ampersand is the bitwise AND operator. Now, so when implementing this, we can see that if we compute these different MERS protocols and store them into a vector in C++, these are the timings we get. So we can see that the take-home message is that Randstrobes is about 1.5 to 2.5 times slower than K-MERS. The number of strobes affect the runtime slightly. We can see that from these protocols going from 2 strobes to 3 strobes are slightly faster, as we can see in this example. However, window size does not really matter that much. So it seems that the compiler is very efficient at computing this minimum across the contiguous block of values in memory. So we can see very few small difference between a fairly small window size and a fairly large window size. So this would be the minimum offset and maximum offset. Which is very encouraging, meaning that they are sort of competitive also in these in real life scenarios. So now we want to evaluate the quality, how well did this perform not only in runtime. So we compare Strobemers to K-MERS and spaced K-MERS. I want to make a disclaimer. We do not aim to compare against sampling protocols, because K-MERS protocols are inherently something different than sampling protocols. We can actually apply sampling protocols to any of these K-MERS, spaced K-MERS, and Strobemers. With that said, okay, so let's continue to look at the context where we want to compare these. So let's say we have 2 sequences, sequence 1 and sequence 2, with 4 mutations, substitutions, and 2 deletions. Now, let's say that these are the shared K-MERS across these 2 sequences. We want to evaluate the protocols in terms of how many matches, or the fraction of matches that they produce, the total sequence covered by these protocols, the total match coverage, which is identical for K-MERS. I will soon show when they're not identical. And the sizes of gaps, and here we use the E size of gaps, meaning that we pay more attention to larger gaps. And these are regions where we have no match coverage. Looking at the spaced K-MERS and Strobemers, these metrics are, of course, the same, besides the difference that sequence coverage is really all the sequence that are covered by matches, while match coverage is more loosely defined as the leftmost to the rightmost position of all overlapping matches. And the gaps are where there is no match coverage. Okay, so if we simulate 2 strings of length 10,000 with some both mutations and insertion deletions of the same probability and independently at random, and we compare K-MERS to spaced K-MERS and Randstrobes, where we isolate or fix the length of subsequence sampled to 30 in each of these protocols. And we have for 3 different set of strings of different identity, 99%, 95, and 90. What we can see when looking at these metrics is that K-MERS in general produce the highest fraction of matches. But as we saw in our example, these matches are usually very clustered. And if we instead look at Randstrobes, we can see that it performs the best across various sequence similarities in all of the other metrics, so meaning sequence coverage, match coverage, and expected gap size across these 3 different similarities. Now, this is great in terms of generating matches, but what about the other aspect? How much do we trust a match? Is it going to be unique, or will it match everything? So we looked at the number of unique K-MERS, spaced K-MERS, and Strobemers that are extracted from the 3 largest human chromosomes. And we fix here the K-MER length for each of the protocols naturally, because larger K-MER will produce more unique values. And it turns out that for somewhat reasonable sizes of K, larger than somewhere 20 to 24, we see that Strobemer protocols, they actually produce a larger fraction of unique matches as well on the human chromosomes compared to k-mers. And this is somewhat surprising. So this means that Strobemers are not just more efficient at finding matches when there are mutations in strings, but they also produce more unique matches in this biological context, which is sort of related to both sensitivity and precision. And if we look at real data, so we looked at 1,000 Oxford nanopore reads mapped to the E. coli genome. And here the reads are fairly noisy, differing in indels and mutations. And this is due to sequencing errors and biological differences. Ignoring the exact details in the interest of time, but we roughly looked at how much do the matches of these protocols cover on the read. And we could see that in general, the matches, we have a much higher match coverage across for Strobemer protocols compared to k-mers. The other aspect is the number of matches. And we looked at the number of distinct matches across the reads, meaning that where sort of we merge overlapping Strobemer matches and k-mer matches. And we could see that the Strobemer matches also are much fewer. This means that in general, Strobemer protocols produce longer contiguous matches on the reads to the genome, which is a beneficial thing to do in terms of when evaluating candidates. So here I presented a new sort of construct to do sequence comparison that shows promise in various applications. Strobemers are used to find, can be used to find similar regions between sequences, are less sensitive to k-mers than for various mutation rates. They are both sensitive in finding matches across small gaps and mutations, while remaining at high precision in the terms of the uniqueness of a match. The paper is currently on bioRxiv, and there are some current work in implementing this in compiled languages from myself and others. And so future work remains to sort of explore where we can find use cases of Strobemers, for instance, read alignment, overlap detection, genome assembly, etc. And then there are some theoretical future work that needs to be planned out or be investigated. For instance, can we find optimal parameterizations of the Strobemer protocols for various mutation rates? What if we vary the size of the strobes depending on some protocol, or the window size, etc. So I want to acknowledge Wei Chen for informative discussion about fast hashing of RAND strobes in compiled languages, and many other colleagues for informative feedback on an early version of this manuscript.